Hi, everyone. Welcome to this session. This is the last session that you will be attending in the senior group. And we are going to close up your whole program with geometry. Now, you've already had a lesson in geometry, and most of the problems in that lesson were dealt with the earlier aspects of geometry, namely the geometry of a triangle and the geometry of quadrilaterals like parallelograms and so on. And now today we are going to move away a bit from that kind of geometry and go into circle geometry and as well as similar triangles and whatever else that goes along with that. So I don't know about you, but I find geometry very fascinating. It's one of the most creative aspects of all of school mathematics because it makes you think and find strategies to solve sometimes seemingly impossible problems. So I'm sure that you are going to enjoy this session very much. So let's go to the very first problem. But before that, I think the key point in geometry is that you should know the statements, and not only know, but you need to understand the statements of all the theorems. In other words, if you have a certain scenario, a certain configuration where there are some facts which are given, you can make conclusions from that figure or from that configuration, right, based on the information which is present there. So geometry does that. It makes conclusions from given data. So you need to know all those theorems which do precisely that. They make conclusions from given data. But I'm going to go over those theorems anyway when we get to them. So just to recall for you what those theorems were. So let's get on to the very first problem. The first problem, as you can see, says that AB is the diameter of the semicircle that is given there. So AB is the diameter, and AB is equal to 10. As you can see, this AB, its length is 10. If the area, so the area of this triangle is given, find the perimeter of triangle ABC. All right, so we know that AB is a diameter, 1, and we know its length, 2, and we know the area of this triangle. So there are 3 things that you know, and you are asked to find the perimeter. Now, so what do you mean by the perimeter? The perimeter is is a sum of the sides, the total distance along the sides. So we've got one side here, and then you have another side which you don't know. Let's call it A, and then there's another side here which is B. So essentially, you need to calculate A plus B plus 10. That is the perimeter. So that's the problem. Okay, so as we said, we'll call the remaining 2 sides A and B. Okay, now AB is a diameter. So straight away, we've got a configuration. You've got a circle, you've got a diameter, and something should strike you straight away that the angle in a semicircle is a right angle. In other words, if you've got a diameter of a circle, the angle that diameter subtends at the circumference. That means if you take any point on the circumference and you start from one end of your chord, in which case it is the diameter, and go up to that point, in this case it is C, and come back to the other end point of your chord or your diameter, an angle is created, and that angle is a right angle, which I have shown. So in fact, this triangle is a right angle triangle. Okay, so now let's go back. We are given that the AB is 10, so we know the hypotenuse. So in a right angle triangle, we have named these 2 sides, so straight away the theorem of Pythagoras kicks in, and we know that the sum of the squares of the two sides, the lateral sides, is equal to the square on the hypotenuse. That's the theorem of Pythagoras. So that is what I've got here. A squared plus B squared equals 10 squared, which is 100. So the diameter is flat and the other two sides are as shown. Okay, so that's the first fact which we have used, right? Now, the area of the triangle is 11. And the area of a right angle triangle, that's very easy. The area of any triangle is half base times height. And the base in this case, the 90 degrees is here. So we have to regard this as the base and that as the height, or even otherwise that as a base and that as height. And the area is half A times B, and half base times height is equal to the area. But we know what the area is. So half AB is equal to 11. So that gives you now two equations and two unknowns. And normally you will say, well, I'm right there because I can now solve for those two numbers, A and B. And the standard method is find one in terms of the other and substitute, and you will have eliminated one of the unknowns by substituting. So here, where AB is equal to 22, if you multiply right throughout, so B, or A at least, is equal to 22 divided by B. All right, so you can do that. So A equals 22 divided by B, and sub it in here. And then you'll have only B's in this, and you can solve for that. And then having solved for B, the usual method is solve for B, and then you substitute it into one of the equations, and you get the value of A out, and then we can calculate A plus B. What the problem is that when you substitute this, you're going to get a fourth power equation, which can be solved, but it has a lot of square roots in it and all that. It becomes very complicated. And then when you try to work out A in terms of that, now you have the value for B, and you can work out A, which is even more complicated. And then you have to calculate A plus B, because the perimeter is A plus B plus 10. Also, what we really need to do is to find A plus B. So that is really the issue. Right. But it's important to notice that we're not asked to calculate A and B. We're asked to calculate A plus B. So why should we go and bother trying to find A and B? We might as well try to calculate A plus B, right? And that, a little bit of thought will say, I have to square it because I have an equation which has A squared plus B squared in it. And when you square it, you use a formula for the square. And then if you rewrite this so that you get A squared plus B squared, which we know, right, in the front. So you can substitute for A squared plus B squared is 100, as you can see. And then the middle term is 2AB. But we know AB, a half AB is 11. So AB will be 22, and 2AB will be 2 times 22, which we've got here. And then when you simplify that, you get 144. So A plus B all squared gives you a nice, beautiful number. No square roots or anything, because you know the square root of 144 is 12. So A plus B is 12. And that's exactly what we wanted. Once we got A plus B, we can substitute A plus B is 12 here. And then the perimeter comes out straight away. It's 12 plus 10. As we can see, the perimeter is 12 plus 10, which is 22. So that's the answer to the first problem. We move on to problem 907 of the book that we are using. It reads as follows. Well, first, let's have a look at the picture. Always nice to look at the picture to sort of get a feel of what the picture is. You've got a large circle and you've got a small circle, and you've got 3 lines which are drawn, and 2 of those lines are chords. This is a chord of the large circle. So is this line here. It's a chord of the large circle. And you've got one line which goes right across. Okay. and it cuts the small circle at D, but there's another point here on the large circle it goes through. What does it say? There's two circles intersect at A and B, as we see. They intersect here and they also intersect here. The center O of circle ABC. So the circle here, ABC, is that circle, the circle that goes through A, B, and C. And the center is O. So O is the center of the small circle. And it's on the circle ABP. So it's on the large circle. All right, so this is the center of the small circle. That is the important thing. Now prove that PC, this PC, bisects angle APB. APB. In other words, this line here divides this whole angle into two equal parts. So the question is to prove that these two angles here are equal. So that's the goal. How do you prove that these two angles are equal? All right, so let's try this problem. Okay, what do we have? We have that O is the center of the small circle. So why don't we draw the O is the center, so we can get, means that OA and OB are radii. So let's draw OA and also OB. And they are radii, so which means that the radii of a circle are equal. So now we know that those two lines are equal. Now remember, we're trying to show that these two angles here are equal. All right. And you'll notice that you got two lines here. These are chords. AO is a chord of the large circle, and OB is a chord also of the large circle. So you've got two chords of the large circle which are equal. So immediately there should be some reminder of a theorem which speaks about equal chords. And what does that theorem say? It says that if you've got equal chords in a circle, they subtend equal angles. So there's an important theorem which says equal chords subtend equal angles at the circumference. Okay, so before we go on, let's try to understand what you mean by subtend. It's a very important concept. So I'm just going to briefly explain what subtend is. So move this thing up here. Now, when you got a circle, and if you got a chord, now remember a chord is a straight line which joins 2 points on the circumference. So I take 2 points and join them, right? Now, if you start from one end of that chord, like I'm doing now, and go up to any point on the circumference, and then from that point you go to the other end of the chord, what happens is that you have an angle formed, this angle here. So when you go up here and you come down, there's an angle formed. This angle here is said to be the angle subtended by that chord which we started off with. So the way to find out the angle subtended by a chord, you start from one end of the chord, go up to the point in question, and go back to the other end of the chord, and there's an angle created, and that is the angle subtended by the chord. So this theorem says that equal chords, so if I take this chord here, right, and I ask myself, what angle does it subtend at the circumference? Then it means that we are moving from one end of the chord and we go all the way to a point in the circumference, then that's the other point in the circumference. And then you come back to the end of that chord, you get this angle here formed. This and that creates that angle. So that's one of the two equal chords, and the other equal chord is this one here. The other chord that is equal to this is that one. So if you start here and do exactly the same thing, go to the point of the circumference and come back to the end of that chord, then you create this angle here. And these are equal chords, and they are equal angles at the circumference. So these angles will be equal. And that's exactly what we wanted to prove, that these two angles are equal, that this line here bisects this angle. So the proof is almost immediate if you know that equal chords subtend equal angles at the circumference. And if you want to know how to write out the proof, we can do it quickly. Sorry, let me just get to black. Required to prove angle APO, angle APO is equal to BPO. That's what you mean by bisect. Right. And the proof, and let's start from where we said. We started out by saying that OA is equal to OB. You have to give a reason for that. The reason is radii. Right? And then you say, but OA and OB are equal chords. In the large circle. They don't normally use the word large circle. They will say the circle which goes through A, P, and B, 3 points on the circumference. The circle APB. Right? And then you say, you make the statement here, equal chords subtend equal angle to the circumference, and therefore that angle equals that angle, as I said earlier on. So that is how you would prove that. You can finish this thing off the way we did. You make that statement, and then you can say that therefore this angle is equal to that angle. Right? And that is really what you wanted to prove. Okay, so that takes care of that problem. Before we tackle the next problem, I need to state a number of theorems, circle theorems, which you should be familiar with and which will be used to solve this problem. So the next problem is quite a deep problem. So let us just recall first the theorems that we need. Okay, now when you have a circle, I've already told you what you mean by subtends. So suppose you got a triangle, right? If you got a triangle has got 3 vertices. There is always a circle that contains the 3 vertices. Right? Now, let's see why that is so. If you got a triangle, right? It's got 3 vertices, 1, 2, 3. And there's always a circle which contains all 3 vertices. The way to draw that circle is quite easy. You have to draw the perpendicular bisectors of 2 of the sides of the triangle and where they meet, that will be the center of the circle. So I'm saying that when you take these 3 points, if you take the 3 vertices of the triangle, I claim that there is a circle which contains all those 3 vertices. And to do that, you draw the perpendicular bisectors of the sides. Take any 2 sides and draw the perpendicular bisector. A line which is perpendicular to it and also bisects it. So there's another perpendicular bisector. This point is the midpoint here, and this is 90 degrees. This point is the midpoint here, and this line is 90 degrees to that. Where these 2 meet, that will be the center of the circle, which contains all these 3 points. All you have to do is to put your compass point here and find the distance from there to there. When you draw the circle, you'll see that it contains all the 3 points. Now, there's only one circle because these 2 lines intersect in exactly 1 point. So there's only one circle that contains all the 3 vertices. So if you got a 4th point, that point need not be on that circle. It could be on the circle, it could be outside the circle, it could be inside, because there's only one circle. Once you draw it, you got another point, you don't know whether it lies on that circle or not. But if that 4th point lies on that circle, then the 4 points, that means there is a circle that goes through those 4 points. If that 4th point, when you draw the circle and you see that the 4th point actually lies on the circle, then you say that the 4 points are concyclic. You use the word concyclic. 4 points need not be concyclic. Con means together, cyclic is circle. So together, those 4 points need not lie in a circle. But when they do, you say it's concyclic. And there are some very good tests to find out whether a circle is 4 points are concyclic or not. Okay. But firstly, before we do that, we see a lot of properties of cyclic quadrilaterals. In other words, quadrilaterals whose vertices lie on the circumference of a circle. Right. And such quadrilaterals are said to be cyclic. So whenever you have a cyclic quadrilateral, there are lots of important properties that a cyclic quadrilateral has. Right? Now, here, if you a quadrilateral, of course, has got 4 vertices. So if you take let me just use black here. Right. So you've got the 4 vertices are concyclic. That means there's a circle that goes through all those 4 points. Then the important thing about one of the things about a circle is that angles in the same segment are equal. What does that mean? When you have a circle and you take any chord of that circle, then what happens is that, let me just take this thing out, or maybe not. If you have any chord in a circle, then that chord subtends equal angles at the circumference. What does that mean? It means that if I take 2 points, a random 2 points on the circumference, and I look at the angle subtended by that chord at the first point, that angle there and then you have, take any other point on the circumference, and you find the angle subtended by that chord, by the same chord, at the circumference, it turns out that these angles are always equal. A very interesting property of a circle. Any chord, it subtends equal angles at the circumference. Okay. Now you got 4 points here. So if I complete the cyclic, the quadrilateral, or complete the quadrilateral, then you notice that all the sides are all chords of the circle. Right? This is also a chord. So it means that this chord here, it subtends equal angles at the circumference. So when you look at the angle that it subtends, comes down here and goes up there, and the angle that you are speaking about is this angle here. This angle is the angle subtended by that chord. I'm focusing on this chord here. The angle subtended by the chord at this point is equal to the angle subtended by the same chord at this point, which means that those two angles are equal, right? So I'm going to put like that. See? So if you got a quadrilateral and you got an angle here like this, it's easy to find out which side subtends that angle, right? You see that one side here, this is one side. You look at the two sides which embrace that angle, and then you'll go from one end of that, draw that angle. When you draw that angle, you'll see the chord that subtends that angle. Okay, these are all important points. So like this now, for instance, if I look at this point here, that angle is subtended by this chord here, because this arm finishes up there, this arm finishes up there. So these 2 points become the chord that subtend the angle, and that chord subtends this angle here as well. So these 2 angles are equal, right? So like that, you have those angles will also be equal. So this is what we are saying here. But in the first statement, I am saying the converse of this, namely, if you know that any one of these, suppose suppose you got a quadrilateral, right? You don't know that cyclic is that quadrilateral cyclic, then an easy test, a very easy test, is to see if any side of that quadrilateral subtends equal angles at the other 2 points. If you can conclude that, then you got a very powerful result, because suppose I see that this side here, for instance, subtends equal angles at the other 2 points. Suppose you know that those 2 angles are equal, namely, the angle subtended by this side here is you go up from one end and you come up to the other end. That's the angle. And from here, if you go up to that and come to that, you get the same. Suppose you know that those 2 angles are equal. Then you can conclude there is a circle which goes through all those 4 points. Those 4 points are concyclic. I told you 4 points need not be concyclic. And once you know that a circle goes through those 2 points, you have an imaginary circle now. You can make a lot of conclusions. Just from the fact that these 2 are equal, you can make a number of conclusions. You can say those are equal. And you can also say those are equal, right? From what I told you earlier on. And then you can also say that angle there equals that. Because all the 4 sides will subtend equal angles at the circumference. Just from knowing the red, you got a lot of other conclusions. So that took a long time, but it's a very important consideration. Okay, now if you go on to the next theorem, right, here, this theorem says that if you got a tangent to a circle, if you got a tangent to a circle, then at the point of contact, there's only one point where the circle contacts this, the tangent contacts it. At that point, if you join that point to the center of the circle, then you have a radius. Right? So let's take this thing here. I think this one here you know quite well. If you've got a tangent, it's a line which just touches the circle, right? So this is the point of contact here where it's contacting. And then if you draw from that point, if you complete the radius, in other words, I join this to the center of the circle, then this radius is perpendicular to this tangent. A radius is always perpendicular to the tangent at the point of contact. So that's the next theorem that we state. The third theorem we state is the third theorem states is that the exterior angle of a cyclic quadrilateral is equal to the interior opposite angle. Okay, now what is the meaning of that? What it says there is that if you have a cyclic quadrilateral, in other words, you've got a circle that goes through all the 4 points, right? Then, and if you draw that quadrilateral, then you can, an exterior angle is obtained by extending any one of those lines like that, right? A little bit more. And then you get a new angle formed from your original quadrilateral. So this quadrilateral is cyclic because there's a circle which goes through all these 4 points. Then it says that this angle here, when you extend it, a new angle is formed, namely this angle here. That new angle is equal to the interior opposite angle. In other words, this angle here is right next to this, it's supplementary to this angle here. But the angle which is opposite that is what this angle is equal to. This angle and that angle, opposite angles of a cyclic quadrilateral are supplementary, right? That's one of the theorems which I'm not stating here. But these two are also supplementary, which means that this is equal to this. So that's the next important theorem. And then yeah, so I think we've stated all the necessary theorems. So let's go to the problem in question. Mm. All right. So the problem that we now are going to tackle, are going to tackle is the following. You have this diagram here, and it's a little bit cluttered. So let's see what is being said here. The inscribed circle of a triangle. So you got a triangle, ABC, ABC, and you can see a circle, and that circle is tangent to all the 3 sides, right? There is a circle like that, which is tangent to all the 3 sides. If you want to know where the center is obtained by bisecting any 2 angles and seeing where they meet. You halve 2 angles and you see where they meet. That is the center of the inscribed circle. Okay, but we're not really interested in that right now. So there's an inscribed circle and it's called an incenter, the center of it. It touches the sides, the 3 sides of the triangle at the points D, E, and F, as you can see. This is where the points of contact are, right? And then they say, let P be a point. You got a point which is outside the triangle, there like that. And it is given that P and A are on the same side of BC, as you can see. BC, A is on that side, P is also on that side. But angle PFE equals BCA. So you have PFE, this angle here. Let's just draw that. This full angle. That angle, PFE, equals BCE. So it's equal to that, right? And then, so that's BCA. Angle PEF equals angle ABC. So let's have a look at that. PEF, I put double lines there, equals ABC. All right, so we have indicated those angles. Now, just those facts are given, and you're asked to prove that P, I, and D lie on a straight line. That means if I join PD, right? You can only draw one line through 2 points, join PD. There's no guarantee that I is on that, but you're asked to prove that I is on that line. Right? They're all three of them lie on the same straight line. Okay, I just want to point out here in this diagram here, you can see that this blue line and this double red are two angles of a triangle. Those two angles are equal to two angles of the small triangle. Right? Now, there are two things you can say about that. One is that the small triangle is similar, the small I mean is PFE, is similar to triangle ABC because two angles of one triangle are equal to two angles of another. That makes those two angles similar because the third angle, namely that one, that's the third angle in this large triangle, triangle ABC, and the small triangle, the third angle, will have to be equal because the remaining two are equal. So these two triangles are similar. That's one conclusion. Okay. So, all right, so this is where we are. But now you will notice that the small quadrilateral here, the quadrilateral, you got those two angles are equal. And what I just told you now, you will see that this angle here is an angle inside the quadrilateral that I'm looking at. And to create that angle, this side here goes up and it comes down like that. It means that this side here subtends that angle. And the same side, to create it, you go up there, subtends that angle. So, in other words, this side of this quadrilateral subtends equal angles at A and P. And the theorem which I just told you means that there is a circle that contains all those 4 points. So there is a circle that contains the A, P, F, and E. Right. This quadrilateral that we have is cyclic. Okay. So that's the conclusion. So let's just go into my other diagram here. Okay, we've just said that A, P, F, and E form a cyclic quadrilateral. The reason is one of the sides of that quadrilateral subtends equal angles at the other 2 points. Therefore, it's a cyclic quadrilateral. Okay. Our goal is to prove that P, I, and D lie on the same straight line. Right. I'm just analyzing the whole thing now at the moment. Now, just hold that thought that these 4 vertices, A, P, F, and E, are concyclic. Now, I want to bring in the center, the in-center, into play. And I also know what I told you earlier on, these are the points of contact. So if we join this, we know that it's perpendicular. If you join the center to a tangent, these are tangents here, because that is what you mean by an in circle. we know that the radius is perpendicular to the tangent at the point of contact. So this angle here is 90 degrees, this angle is 90 degrees, and the other angle is also 90 degrees. Okay, so it means that we've got an exterior angle of this quadrilateral. Now let's focus on this quadrilateral here, which has got two red lines, an AF and AE. AFIE. Right, you can see that the opposite angles, this is 90 degrees here. So the other opposite angle there is 90 degrees also, because this is 90. The opposite angles are supplementary. And the conclusion is that this quadrilateral AFIE is also cyclic. So these are the two important things that we have, right? Namely that AP, we'll say AEFP, AEFP, and AEIF, AEIF, these are both cyclic quadrilaterals. Both are cyclic quadrilaterals. So we still don't know, anywhere near proving that A, I, and D are cyclic. I mean, they lie on the same straight line. Okay, so remember, I had earlier on I had this. I think we said that this angle here, that angle was equal to I think this angle here. And we also said that this angle here is equal to that angle there. Now, bearing that in mind, we know something about this angle. It is an angle in the cyclic quadrilateral here. It's actually subtended by PF. This angle here is subtended by PF. You can see PEF. So it's this side here subtend this angle. And because we know it's cyclic, this PF will subtend that same angle at A, PAF. So these angles here are equal. Let me just use red here. All right, so those angles are equal. And now we were given that this angle is equal to this angle, and this angle is equal to this angle because it's cyclic. This means that when you join PABF, now look at the picture there, PABF, you will see that the alternate angles, that angle and that angle are alternate angles. Now, when you got alternate angles are equal, then you can conclude that the lines are parallel. This was one of the theorems I stated earlier on, but I forgot to show it to you. If you know that this angle, the Z angles, if you know these angles are equal, you can't draw this picture like that, because then these lines will have to be parallel. That's the only time these angles are equal. So the long or the short of the story is that that line there, let's put a red there. That line is parallel to this. The topmost line is parallel to this. Okay. Now, if you join I and D, that's also 90 degrees. Because this is tangent here. So you know that this angle here is 90 degrees. Now, here's something very interesting. The angle IPA, this is not very easy to see. IPA. API, right? I claim that that angle is 90 degrees also, API. Now, what's the reason for that? Now, follow the argument carefully. Remember, we said here that both these are cyclic quadrilaterals, right? Now, if you focus on AFE, if you focus on these points here, A, F, E, we saw that the circle that contains these three green points, it contains P, because that thing was cyclic. And it also contains I, because we said that those 4 points are concyclic. So it means there is one circle that contains all 5 points. The circle that goes through these 3 points, there's only one circle. It contains P and I. So there's one circle that goes through all those 5 points. So those 5 points are concyclic, right? Now, what does that mean? It means that this PI is going to be a chord of that circle. PI is going to be a chord of that circle, right? Right. And these 4 points are concyclic, all 5 points. Right. Now, AI is also a chord of the circle, because all 5 points lie on the circle. But watch, IFA is 90 degrees, because this line is perpendicular to this. So IA is a chord which subtends a right angle at F. So IA has to be the diameter of that circle. IA is the diameter of the circle that one circle that goes through all those 4 points, which means that IA subtends 90 degrees at even P, right? So angle API is 90 degrees. That is what I said earlier on. I claimed that it's 90 degrees. So angle API equals 90 degrees, and angle CDI is also 90 degrees. CDI and API, they're both 90 degrees, right? And these lines are parallel. We saw that. So when I take PI and produce it, this lines are parallel. This is 90 degrees now, API. So and this line is parallel to this. If I take PI and produce it, it must be perpendicular to CD, because these are parallel lines. That is 90. But ID is also perpendicular. So that's enough to say that PI and D lie on the same straight line, because ID is perpendicular and PD is perpendicular. So the only way that can happen is PI and D lie on this transversal. So that is a very long way of doing this problem. Okay, but it involves a lot of circle results, and it's rather it's a quite a difficult problem. But I hope when you go through it, I hope you understand it.